But there was a surprise long time ago. There was an experiment, the double-slit experiment, that showed that not only light, but also electrons have this wave-particle duality, right? The experiment threw electrons through a double slit, and while we could expect, if they were particles, that we would see this double slit again projected on a second screen, there was an effect of interference pattern. So we see on the screen, we see a pattern that corresponds to wave. So this was quite a surprise. So maybe every equation we had been using was not totally correct.
Mm-hmm.
And well, here we have Niels Bohr lecturing about quantum mechanics on Iowa, precisely explaining this experiment. So we are at the beginning of a new area. We are jumping from the classical to the quantum reality. But this quantum reality looks like something very modern, almost science fiction, but we could think it's quite old. It all started in the past century with Planck, who introduced the concept of energy quanta to explain black body radiation, right? And he already proposed that energy could be emitted in discrete units. And this idea of having energy in discrete packages or units was around also, of course, in the theories of Einstein, of Bohr, who developed the atomic model with quantized electron orbits, de Broglie, who proposed the wave-particle duality for matter, and Heisenberg, Schrödinger, and so many people. We can see many of these people in this Congress in Solvay in 1927. We can see most of the main characters of this revolution, which is nowadays, it looks a bit old, right?
Mm-hmm.
And here, but still we maybe don't understand completely, right? We see the Schrödinger cat, and well, the cat is here or is not here. What's the mystery? So we can make some jokes about it, about your cat. I have good and bad news. So indeed, maybe the truth is that we are a bit in both worlds, right? Classical and quantum. Already this was observed by Feynman. Nature is unclassical, and if you want to make a simulation of nature, you'd better make it quantum mechanical. It's a wonderful problem because it doesn't look so easy. And here we are, still trying to understand it. So there is a lot of, at the beginning, there was a lot of discussions about classical versus quantum world, but maybe we have to think in a different way. It's like not about opposing two different worlds, but trying to understand nature with both phenomena at the same time, the wave particle phenomena. So here we have this picture where we have on one side the solar system, right, celestial mechanics, and on the other side the subatomic particles. So it wants to illustrate this classical and quantum world. So maybe they are not so apart. I mean, feel free to ask me.
Yeah, I have a quick question. Yeah. Most of the time we talk about quantum mechanics as being more fundamental, or all of the time, that the classical world emerges from the quantum. However, when speaking about the standard model, we start with the classical Lagrangian and then we quantize it. So we start with something classical and then we apply a procedure. Now there's a criticism that that's going about it backward. What we should be doing is starting from something quantum and you recover the classical. So I want to know how it is you respond to that. How do you think about that?
Well, this is a very good idea and very good question, and we don't need to take a decision about what is better, because we can do both. Indeed, what you suggest is a very good idea that has been implemented. You could first apply the quantization procedure, something I still didn't explain, but I will, and then apply it again somehow. And then somehow you can start from classical to quantum and then recover the classical. So you can do the quantization. I'm not going to talk about this point. I mean, I didn't prepare the slides about this, but this has been done. So the problem is that you don't always recover where you started from.
Right. So it's not one-to-one.
Yeah, and the reason why is that I could say quantization, the process is very capricious. It's almost an art. There is not a unique way to do it. You have to make choices, and depending on your system, this may or may not work. It's a kind of art, I could say. So what you are suggesting is a very good idea. I think we should approach this towards the end, because I still didn't explain, the first quantization. But what you're suggesting is something that people have been trying to do, and in some cases it works very well.
Great.
In some cases it doesn't work, because in some cases not even the first quantization works. And so here is a picture of what we want to think about. Now, right now, I'm just trying to explain if our reality is classical or quantum. I want to just first answer this question without explaining how to go from one to the other. So here we have like two pictures of a girl walking up. On one side, we have a ramp. On the other side, we have some stairs. And we could think of this as an illustration of reality being at the same time classical and quantum. These stairs are a little bit the symbol of the packages of energy that we see in the quantum world, right? So in a way, we shouldn't think about, well, of course, if you have to go up, you have to decide if you take the ramp or the stairs. But maybe we could take both, the ramp and the stairs. Indeed, let's think of this as a picture, as an art. Let's think, as I was talking about art, let's look at some pictures, right? Here we have some pictures of Impressionists, right? And here we have, if you come to Barcelona, you should come to Barcelona. Please come to Barcelona. You'll see this wonderful, have you been here?
Not yet, but at some point I'll be coming to the University of Barcelona.
You should. So if you come to Barcelona and you have the opportunity to see Gaudí art, you'll see that it's formed by little mosaics, but little pieces of art. But from far away, you don't see that this is formed by little pieces of mosaic. So this could be the classical and quantum world at the same time. In a way, we could be running up the stairs at the same time as we are running up the ramp. So we are combining classical and quantum world in a way. But this is like a modern approach. This is more like, well, not so modern, because Einstein and Feynman were also pointing to this to coexistence of both realities on the same. But if we are like sometimes to make difference between systems. If we think about classical systems, we are thinking about Hamilton's equations. And on the other side, if we're thinking about quantum systems, then the equations are Schrödinger equations, where here we have the symbol of the wave, right?
Mm-hmm.
So the evolution, again, both of them, there are many patterns in common. There is an evolution, but it's an evolution of not trajectory of a particle, but probability of trajectory of a wave.
Yes.
And we could, and well, this is extracted from somewhere on the internet, we could indeed summarize. We could take, for instance, as you were suggesting, let's take a classical system, the harmonic oscillator, okay? And we could just replace the piece by the partial derivative of x and the x by themselves. And this gives me the quantum version of this harmonic oscillator, okay? And this idea is a little bit the idea that you were suggesting of going from classical to quantum, but we need to understand what we are getting. In a way, what do we need to understand? On one side, we have classical systems with observables. Observables are the observables of the classical systems, the energy of your system, etc. This could be potential energy, whatever. And these are functions. This infinity M is just functions on, I would say, a manifold. But if you don't want to think about a manifold, think about the Euclidean space. These are just functions. And there, when I have classical systems, there is the dynamics is governed by a bracket, which is the Poisson bracket, which I will talk about. And now I'm just presenting the ingredients, and then I will go deep into them. On the other side, we have quantum systems. Instead of functions, these observables, we have operators on a Hilbert space. This is what we want. And instead of the bracket, we have the commutator of these operators that satisfies this formula here. You can see it. And, well, here you have another, you see a mathematician, right, struggling to see how to go from one side to the other. Quantization is the art. What is the definition of quantization? Quantization is the art of crossing the bridge from classical to quantum in this picture.
Mhm.
So assigning from classical system, a quantum system, to functions, we need to associate operators of a Hilbert space, and to the Poisson bracket, we need to associate a commutator. And we think that if we go back to Dirac at the beginning, people thought this was pretty simple because we know what we want, but it's difficult to get it. So we are now trying to see how to go from one side to the other side. It looks simple, but the truth is that this is the joke from Shapiro. I still don't understand quantum theory. So, and then this reminds me of this famous. Okay, so yeah, so this is the typical sentence we all heard about, that nobody understands quantum mechanics, that Feynman says, and he said that in a class, apparently, right, where he's mentioning that, okay, relativity was very complicated, but at least there were more than 12 people could understand it, but quantum mechanics, maybe nobody can understand.
New update. Started a Substack. Writings on there are currently about language and ill-defined concepts, as well as some other mathematical details. Much more being written there. This is content that isn't anywhere else. It's not on Theories of Everything. It's not on Patreon. Also, full transcripts will be placed there at some point in the future. Several people ask me, "Hey Curt, you've spoken to so many people in the fields of theoretical physics, philosophy, and consciousness. What are your thoughts?" While I remain impartial in interviews, this Substack is a way to peer into my present deliberations on these topics. Also, thank you to our partner, The Economist.